All right, so this video is going to focus on net ionic equations. We're going to look at them initially in the context of precipitation reactions, but net ionic equations can be written for any chemical reaction. You are most familiar with molecular equations as they contain the complete formulas for your reactants and products on both sides of the equation. The complete ionic takes any strong electrolyte that is present in the molecular equation and dissociates it into their respective ions. So in this particular example, silver nitrate would dissociate into silver plus and nitrate minus. NaCl in aqueous form would dissociate into Na plus and Cl minus. AgCl would remain intact as it was a solid and therefore a non-electrolyte. And sodium and nitrate would also separate into Na plus and NO3 minus. I didn't write the AQs after each respective ion, and the main reason I wrote them in the initial equation was just to help you remember which compounds could be dissociated, which ones were aqueous and contained a ionic compound. Remember, your ionic compounds, your 6 strong acids, and your liquid metals are your only possible strong electrolytes. If we look at our complete ionic equation, we will see that there are sodium ions on both sides as well as nitrate ions on both sides. Those particular components did not get transformed as a result of this chemical process. So they're not going to be included in our net ionic equation because that only shows the components that underwent a chemical change. Sodium and nitrate ions, in this particular example, are known as spectator ions. They were a part of the compounds that provided the ions which underwent a chemical change, but they themselves did not get transformed. So here we have an equation with NiNO32 and sodium carbonate, Na2CO3, reacting to form nickel 2 carbonate, NiCO3, and sodium nitrate, NaNO3. So first thing we need to do is to balance this equation. We have NIs, one of each on both sides, but we have 2 nitrates on the reactant side, and we only have 1 on the product side. So we're going to put a 2 in front of NaNO3. That's going to help us out with the sodiums on both sides, and we have 1 carbonate ion on both sides. So now we have a balanced equation. To write the net ionic, we're going to use our solubility rules to identify which of these substances are aqueous, and so which ones are soluble, and which ones are going to form solids, which ones are going to be insoluble. Knowing that in a precipitation reaction, you start with 2 aqueous solutions, and you want at least one of the products to form a precipitate, something insoluble. Well, nickel 2 nitrate is soluble. All nitrates are soluble, so that would separate into nickel 2 plus and 2 nitrate ions. Sodium carbonate is also going to be soluble. All alkali metals are always soluble, so that will dissociate into 2 sodium ions and 1 carbonate ion. I believe if you look at your rules for carbonates, you're going to see that they are primarily insoluble, and nickel is not one of the exceptions. So that particular compound is going to stay together as a unit, while the sodium nitrates both contain ions that are always soluble, and so that particular compound is going to split into a sodium ion and a nitrate ion. But because there are 2 of that particular molecule present in the balanced equation, we will produce 2 sodium ions and 2 nitrate ions. Our complete ionic is what you see there. So now we're going to identify any spectators, any ions that are the exact same form on both sides of the equation. And I believe you're going to see that with both sodium and nitrate. So our net ionic equation will be the nickel 2 plus and the carbonate minus 2 producing nickel 2 carbonate. I do not require you to write complete ionic equations. At the same time, I do want to make sure that you understand why some of those ions went away and why those particular compounds were able to dissociate. So you want to make sure that if you want to try to skip over this middle step, that you understand what can be separated and what can't. And the only compounds that can be dissociated are your strong electrolytes. I also do not require you to write the forms of the ions in your net ionic equation. The 2 on the left would be aqueous, the 1 on the right would be a solid. So now we're going to predict products. We're going to use our solubility rules to determine if a precipitation reaction can occur. If it can occur, we need to make sure we balance it, include both our products, and then we're going to write the net ionic equation. If nothing happens, if nothing is transformed, if everything stays in solution and we just had a physical change take place, then we write NR for products and we don't have to balance because there truly wasn't a chemical reaction. So if you remember back from when we did this previously, potassium and iron are going to switch places. And so Fe is going to go off with S and K is going to go off with SO4. So there's our iron and sulfate ions, and there's our potassium and sulfide ions. So again, Fe switches places with K and joins up with sulfur. I believe if you take a look at your solubility rules, you will see that all sulfides are primarily insoluble and that Fe is not one of the exceptions. While potassium and sulfate are going to stay soluble, you have an alkali metal present, and so they're going to stay in solution. If we look at this particular equation, if you were going to write the products as a molecular equation, you would have had FeS up next to the arrow, and you would have had K2SO4 also up next to the arrow. We have one Fe on both sides. We have one sulfur on both sides. We have one sulfate on both sides, and we have two potassiums on both sides. So this particular equation is balanced. We did have a reaction occur. We did have a precipitate form with FeS. So now we can look to see what ions are spectators, which appears to be the potassium and the sulfate. And so now our net ionic equation would just show the iron ions and the sulfide ion, combining to form the precipitate of iron 2 sulfide. In our next example, we have sodium hydroxide and lithium sulfate. So again, we're going to separate those two in their respective ions. They're in aqueous form. They are ionic compounds, so they are soluble. So sodium hydroxide is going to split into sodium ions and hydroxide ions. Lithium sulfate is going to split into two lithium ions and sulfate ion. When we switch sodium with lithium, we're switching to alkali metals, so you should probably already be able to tell just by the fact that we only had alkali metals present with our reactants that there's pretty much no way we can form precipitates as products. Sodium will join up with sulfate, and lithium is going to join up with hydroxide. Now, I did not balance this equation yet, but I don't think it's going to matter whether I balance it because even if I do, if I put LiOH at the top and 2 in front of it, I'm going to have the exact same number of lithium ions and hydroxide ions and sodium ions and sulfate ions on both sides of the equation once I balance out the 2 I put in front of LiOH with the 2 in front of NaOH. So this actually did not cause anything new to form. Everything was soluble, so there were no precipitates. So this is a no reaction. Our last example involves mercury 1 nitrate and calcium chloride. So mercury 1 and nitrate are going to separate into their ions. This is a soluble ionic compound because you have nitrates, and nitrates are always soluble in the presence of water. Calcium chloride, chlorides primarily are soluble. Calcium is definitely not one of the exceptions, so that too will separate out. And so now mercury 1 and calcium are going to switch partners. And I believe when we look at the rule for chlorides, we see that mercury is one of the exceptions, and so that particular compound will form a precipitate. We also see that with nitrates that they are always soluble, so calcium and nitrate are going to stay separated from one another. We have 2 mercury atoms on both sides of the equation. We have 2 chlorides on both sides of the equation. We have 1 calcium on both sides of the equation, and we have 2 nitrates. So this is a balanced equation. We can now look for our spectator ions, which would be the nitrates and our calciums. And so we can show what actually was transformed with our net ionic, the remaining ions, the mercury 1 and the 2 chloride ions, forming mercury 1 chloride.